Now we will see the next question. 3.22. Figure 3.33. That means this figure given in the textbook shows a potentiometer with a cell of 2 volt and internal resistance 0.40 ohm maintaining a potential drop across the resistor wire AB. PD across is AB. A standard cell which maintains a constant EMF of 1.02 volt for very moderate currents up to a few milliampere gives a balance point at 67.3 centimeter of the wire. 67.3 first. Say L1. Okay. 67.3 centimeter length of the wire. To ensure very low currents drawn from the standard cell, a very high resistance of 600 kilo ohm. 600 kilo ohm is put in series with it. Okay, 600 kilo ohm is put in series with it, which is shorted close to the balance point. The standard cell is then replaced by a cell of unknown EMF E or epsilon, and the balance point found similarly turns out to be 82.3 centimeter length of the wire. Centimeter length of the wire. Subdivision 1. What is the value of the EMF which is being measured? What purpose does the high resistance of 600 kilo ohm have? Is the balance point affected by this high resistance? Is the balance point affected by the internal resistance of the driver cell? Driver cell means this is the driver cell. Okay. Would the method work in the above situation if the driver cell of the potentiometer had an EMF of 1 volt instead of 2 volt? Would the circuit work well for determining an extremely small EMF, say of the order of few millivolt, such as the typical EMF of a thermocouple? If not, how will you modify the circuit? So many subdivisions are there in this question. The first one, subdivision A. First is keeping a standard cell and close to the balance point it's shorting. That means when you are exactly measuring at the balance point position, no need to include this high resistance. See, experimentally what you will do to determine the balance point, we will put the high resistance. But when it is somewhat close to the balance point, we will have to exclude the high resistance. For that purpose, we will short this. Then only you can accurately measure the balance point. Okay. So, is a balance point, first case is measured to be 67.3 centimeter when you include a standard cell. Then the experimental cell is included, whose EMF is to be determined. Its balancing length is found to be 82.3 centimeter. So, is asking what is the EMF of the second experimental cell. So, you know that E1 by E2 is L1 by L2. Okay. Now, you are supposed to find E2. E2 is E1 into L2 by L1. What is E1? The EMF of the standard cell is given to be 1.02 volt. Okay, supposed to find E2, E1 into L2 minus. L2 is 82.3, L1 is 67.3. E1 is given, EMF of the standard cell is given in the question as 1.02 volt. This on simplification will give you 1.249. So, you approximate it to 1.25 volt. So, the cell has got an EMF of 1.25 volt. First part is over. Answer is this. Why high resistance is required here? That is to protect the galvanometer from any heavy current for positions far away from the balance point. See, the galvanometer would be very sensitive and it can easily be damaged if current greater than a particular value flows through the galvanometer. So to protect the galvanometer from some high currents, as a precautionary measure, we put one high resistance in series with the galvanometer. Okay? Then balance point affected by high resistance. It is not affected by high resistance because you are taking the length only when the high resistance is shorted. So even if you put 1000 kilo ohm and short it, the balancing point is to be same. Balancing point, how do you get the balancing length here? The balancing length you will get only when the PD across the balancing length is equal to EMF of this, because no current flows through this. When the PD across, because there is a current flowing, PD across this, when it is equal to EMF of this, then galvanometer will show zero deflection. So it doesn't matter really whether you include the high resistance or not, because the inclusion of the high resistance will not affect the location of the balance point. Got this? Yeah. Next one is balance point affected by the internal resistance of the driver cell. This is a driver cell whose internal resistance is 0.4 ohm. Of course, balance point definitely will be affected. Why? Because you see the PD, the EMF is 2 volt. Therefore, PD across the entire wire VAB plus the PD across the internal resistance VR should be equal to this EMF. E driver cell VEB plus V internal. You can just imagine there is an internal resistance R. So PD across this plus PD, forget about this circuit for the moment. PD across this plus PD across this will give you PD across this. Therefore, when you change this, then this has to be changing because this is constant. When this changes, then potential drop across the entire thing will change. So potential drop per unit length will change. VAB by L will change. Potential gradient will change. Potential gradient will change means balancing length will change. That means balance point will get affected. Do you understand that? Yeah. Next one, what will happen if the EMF of the driver cell instead of 2 volt, if it is 1 volt, will you get the balancing point? You will not get the balancing point. Not possible. Why? Because this is having 1.25 volt EMF of the experimental cell. If you make it 1 volt, so PD across the entire thing is supposed to be 1 volt provided internal resistance is 0. So whatever it is, the EMF across or the PD across the entire potentiometer wire will be less than 1 volt in the presence of this, because you see this VAB should be equal to VR. VAB means this. VAB plus VR should be equal to this. Even if you assume the internal resistance 0, if you assume, then PD across the whole thing will be equal to PD across this. But you have to balance 1.25 volt within this AB for this. How is it possible? Because the whole PD available itself is 1 volt. How will you get a segment where the PD is equal to 1.25 volts? See, balancing the galvanometer will show 0 deflection. Galvanometer will show 0 deflection. Only the PD across this will be equal to EMF. But PD across this, how can it be 1.25 whereas the whole PD itself is 1 volt? So the condition is to get the balance point, the EMF of the driver cell should be greater than the EMF of the experimental cell, whose EMF you are measuring. Do you understand it? That is why sometimes you have the galvanometer, practically speaking, when you do the experiment in the lab, sometimes the galvanometer will show same side deflection. Okay, why it shows same side deflection? Because this condition is being violated. What condition? EMF of the driver cell should be greater than the EMF of the experimental cell. So in such cases, what you should do, increase this voltage. Then probably you will get the balancing length. Okay. Then can you use this potentiometer to measure extremely low value of EMF, low value of voltage or EMF of the order of few millivolt? Not possible again. Why? Because if you want to measure the EMFs of millivolt range, the whole PD should be very small. You see, normally we have some 2 volt or something, but you should have millivolt to be of the order of this. So you want the whole AB, you should only have a very small potential difference. So what you should do for such cases, you put a high resistance here, very high resistance. Let this be the potentiometer wire. Okay. AB. You have a galvanometer and you can have this. Because whole PD available between A and B is far less. Why? Because you put a high value of resistance here. So this 2 volt, out of that, the very high voltage will be dropped here. Maybe say 1.9 or something, whatever it is. High voltage may be dropped here. Only very small voltage is dropped here. So because this plus this, I call this as a V series resistance. So this ED should be VAB plus VR plus V series. You put a high resistance, so VS will be very high, so that VAB will be very small. So you can easily measure small voltages. So what is the suggestion? Put a very high resistance in series with the potentiometer wire. Then you can easily measure. In fact, that is how a thermo EMF is measured using a potentiometer. Okay, thank you. Next question. The figure shows 2 volt potentiometer used for the determination of internal resistance of a 1.5 volt cell. The balance point of the cell in open circuit is 76.3 centimeter. When a resistor of 9.5 ohm is used in external circuit of the cell, the balance point shifts to 64.8 centimeter length of the potentiometer wire. Determine the internal resistance of the cell. See, this is a direct question. Determination of internal resistance of a cell using potentiometer. So the formula is capital R into L1 minus L2 by L2. What does it mean? Find the EMF when the cell is open. Maybe you will include one key, leave the key open, experimentally speaking. Suppose the key is open, because it says an open circuit. So this cell will not deliver any current. So whatever is the balancing length is 76.3. Now you close it. That means there is current circulated in this wire also, in this circuit also. Again find the balancing point. It is 64.8 centimeter. What resistance you are including? 9.5 ohm. What is the internal resistance of the cell? Which is not shown here. Maybe you can consider it somewhere here. So formula is R into 9.5 into L1 minus L2, 76.3 by minus 64.8 by L2, which is 64.8. Okay. This on simplification will give you 1.69 ohm. So write it as 1.7 ohm. 1.7 ohm. Okay, thank you.